Welcome in another video. Today we are going to discuss the most common oxidation states of the first transition series, starting from Scandium 21 till Zinc 30. So let's start. So as we can see here, the most common oxidation state of Scandium is 3 positive or positive 3, since Scandium tends to lose its 3 electrons from the 4s sublevel and 3d sublevel. So you know that Scandium, let me write it here. I will just quickly write it. Scandium 21, the electronic configuration of Scandium 21 is argon 18, then 4s2, 3d1. So it loses the 2 electrons from the 4s and 1 electron from the 3d, giving me an oxidation state of positive 3. So this is the most common or even the most stable oxidation state of scandium. Okay, moving to titanium. We move into titanium 22, and we can see here that the most common oxidation state of titanium is for positive. As you can see, the most common oxidation states are marked with blue and the rest with the other color here. So with this color here. So you can see here that the titanium oxidation state, or the most common oxidation state for titanium, is for positive, uh, marked in blue, um, because titanium loses the four electrons, two electrons from the 4s and two electrons from the 3d, giving me a stable oxidation state of 4 positive, and the electronic configuration is similar to the nearest noble gas, which is argon. Here we can see vanadium, it loses the 5 electrons actually. It loses actually the 5 electrons, 2 electrons from the 4s and 3 electrons from the 3d sublevel, giving me an oxidation state of 5 positive and an electronic configuration of argon 18. Easy peasy, right? Here, here in case of chromium, we have two common oxidation states. We have the 3 positive and the 6 positive. Actually, the 3 positive is more stable, and this is actually because of the T2G and EG diagrams. If you electron configure the if you electron configure the the three remaining electrons in the T2G and EG diagrams, you would find a stable sublevel, okay? And if you want me to make a video about it, please let me know in the comments. Okay, and we move into the 6 positive oxidation state of chromium. Why is it stable? Because also it's similar to the argon 18 electronic configuration. How about manganese? Manganese 2 positive is more stable, is one of the most stable oxidation states actually, not as more stable than another, but is one of the most oxidation states of manganese, because you would get 3d5, and 3d5 electronic configuration is half-filled sublevel, with electrons, and when you have an energy level, or sorry, sublevel half filled with electrons or completely filled with electrons, that means you have a stable sublevel. Okay, so 3d5 half filled, stable, good for the metal, okay, or for the metal ion. How about for positive? Again, the reason here lies in the T2G and EG electronic configurations. Okay, how about the 7 positive or positive 7, argon 18? How about the 3 positive in or positive 3 in iron? In iron here, we have the 2 positive oxidation state and 3 positive oxidation state. Positive 4 and positive 6 are not common at all. Positive 3, because you would get a D5, right? A D5 electronic configuration. Okay, how about the cobalt and nickel? You have 2 positive in cobalt and 2 positive in nickel. That lies in the T2G and EG electronic configuration. Even the 3 positive oxidation state also, to be honest, this is also um, a common oxidation state of cobalt. We move on to the copper here, and we actually notice that the 2 positive oxidation state is more common than the 1 positive oxidation state. Although the 1 positive oxidation state has an electronic configuration of the 3D10, right? It has a 3D10. That means this should be more stable than the 3D9. Actually, this is not the only reason. When you have an energy level or an energy sublevel completely filled with electrons or half filled with electrons, this is not the only reason which gives us the stability for the metal ion. You get me? So another reason is the hydration energy. So the hydration energy in copper 2 positive, let me write it, copper 2 positive hydration energy is more than the copper 1 positive hydration energy. And since the hydration energy is higher, in case of copper 2 positive, it gives it more stability, okay? So that means the oxidation state of 2 positive is more stable than the copper 1 positive oxidation state. Okay, we move on to the zinc, and zinc has only one oxidation, one common oxidation state, I should say, okay? That is 3D10. We have some general notes. Scandium has only one or a single oxidation state, as you can see here, the 3 positive, positive 3 here. The highest oxidation state is found in manganese, manganese 7 positive, as you can see here. And finally, in each transition metal, the highest oxidation number does not exceed the number of its group except copper. That means when you look here, you have the highest oxidation state is 3 positive, and the group number of scandium is 3 positive. How about titanium? Titanium group 4b, and you can see the highest oxidation state is 4. Vanadium 5b, and here the highest oxidation state is 5. Chromium 6. Manganese 7. Iron 6, cobalt 4, nickel 4 positive, and so on and so forth, so forth. And when you get into copper, you can see that the highest oxidation state is 2 positive, right? And that exceeds its number, the group number actually, it's 1b, right? So it exceeds it. And this is actually an anomaly. How about the 2b here? Yes, 2b, 2 positive oxidation state. It follows the rule, okay? So, and that's it. See you in the next video. Bye.